All right, we've been talking about what definite integrals are, and we're going to start shifting into talking about how to calculate them and their values. Remember, a definite integral is a number. If you have a function f of x and it's continuous on an interval, a closed interval, a to b, then we know that this definite integral from a to b of the function with respect to x is the limit of the Riemann sums. Remember, we did this, the limit as n goes to infinity, or you can also do it the limit as that interval space, the delta x, goes to 0 of the Riemann sum from k equals 1 to n at f at some constant ck times delta xk. Remember, what this does is this is the height of the rectangle, the width of the rectangle, and we're adding all these little rectangles up. And we take the limit as we get to lots and lots and lots of rectangles, and we get the area under the curve. So the definite integral is a number that's the area under the curve. Now, this takes the area from left to right, from A to B, where A is less than B. So our delta x's are positive because the x values are increasing. But what happens if we switch our order? If we switch our order and we go from B to A, then that's going to give us just a change of sign of the ones we found from A to B. Because now, in this one here, we're going from right to left. So our values from delta x is decreasing, so our delta x is negative. This is the first of a set of rules for definite integrals, and they're on page 269 in your book. And we're going to look at those for this lecture so that you can start working on how to calculate these and how they work. So the first rule is this change in order of integration. Okay, so if you change the order of integration, it just changes the sign. And the second one is if we're taking the integral from a number to itself. Now, if you have a function and you're taking an integral and you're trying to take it from this space to this space, well, that delta x is 0. So when you take the limit of this Riemann sum, the delta x is always 0, so that's 0. So if you're taking the integral and your limits of integration are the same number, then the integral is always 0. That's just a definition for definite integrals. Now what if we have an integral and we've got the constant times our function? Well, we know that this is the limit as n goes to infinity from k equals 1 to n of, or let's use I this time since we have a constant k, of k times this Riemann sum. And we know with our limit rules on page 67 that means we can pull this constant out. Which means that when you have an integral, you can pull the constant out front. So this is a constant rule. If you have the constant in here multiplied times the function, and then you're taking the integral, you can take the constant out front and then multiply it times whatever you calculate the definite integral to be. Because remember, the definite integral is just a number. It's going to calculate out to be a number. There will be no more x's left in there unless your limits of integration involve an x. So that's the third rule, the constants. Now, what about if we have a sum and difference? If we have two functions and they are integrable over this interval from a to b, and we want to take the integral of their sum or their difference. We're just going to do this all in one because it's the same type of thing. You know that that's the Riemann sum, the limit as n goes to infinity from k equals 1 to n of these functions times the delta x. So this is the Riemann sum that it works. Now remember, you've got to be able to relate this integral to the limit of the Riemann sums, just like we had to do the derivatives with the limit of the slope of the secant line. Got to do the same thing. Got to be able to know that definition. So when you use all your rules of limits, you know that you can distribute this to both of these. So we've got the limit as n goes to infinity of the sum of f at ck. Wow, my handwriting's terrible this morning, sorry. And then we know we can split the sum. These are for a sum rule. We know we can split that. And that was, we talked about that at towards the end of the year last year in advanced math. Those sum rules. We talked about sequences and series. I don't need that last one. Okay, so we've split our sum up, and now with our limit rules, we can split the limit. So these are all things that we've talked about in the past. And basically all I'm doing is proving these properties of definite integrals for you. Well, this, we know, is the integral from a to b of f of x dx. And we know that this is the integral from a to b of g of x dx. So that gives us our rule. We've got, if you have the integral of sum or difference, then you can take the sum or difference of the integrals. And that's rule number 4 there, sum and difference rule on page 269. Another rule we've got, if we have the area under the curve f of x from a to b plus the area under the curve of f of x from b to c, then you can combine all of that into one area. A picture will help with this, I guess. So if we've got a and b and c, so the first integral is this one, that's this, and then the second integral is this part here. So if I'm adding those two together, then this is just the whole thing added together, which means we're just going from a to c. Now remember, you have to be careful with integrals because you need to know, are you looking for the area under the curve, or are you actually just finding the number, the integral? Because sometimes that'll be different depending on if it's above the axis or below the axis, because remember we talked about area above the axis was positive and below the axis is negative. And so if you are taking the integral, you have to watch for that. All right. The next property is called the max-min inequality. And what that means is your minimum value, your minimum function value times the width there of your area is going to be less than or equal to your area under the curve from a to b, which is going to be less than or equal to your maximum function value times b minus a. Now, what in the world does that mean? Well, if you have a function and you have a and b, if you take this minimum function value in here, so that's about right here, and you multiply it times b minus a, well, what have you got? You've got the area of this rectangle right here, right? Because the minimum function value gives you the length of the rectangle, and the b minus a gives you the width. So you have this rectangle here. If you have the maximum function value, it's up here, and if you multiply it times b minus a, then you've got this rectangle here. And what this is saying is that this little rectangle's area is smaller than the actual curve's area, which is smaller than this maximum function value rectangle's area. Okay, so you got the little rectangle is less than the function, the curve stuff. All this under the curve here. And the maximum function value rectangle, the big one, is the biggest. Right, if you look at the picture, it makes sense. So you just have to kind of think through that and make sure. So pause for a second and think through this and make sure you understand what they're saying for that. All right, the last one is called domination. And what that means is if you have a function that's bigger than another function on this interval, then the integral is going to be bigger, which also makes sense if you use a picture. So if you have this f of x here and some g of x here, and you're going from a to b, well, because f of x is bigger than g of x, then f of x, the integral is area under the curve, remember, so that makes sense that the integral is going to be bigger for f of x than it will be for g of x, because g of x is smaller. Now, more specifically, if you know that f of x is above the x-axis, it's greater than or equal to 0, then you know that your area has to be greater than or equal to 0, because all this is doing is using g of x equal to 0, but that's a more specific case. Now, those are the properties of definite integrals. You need to make sure you know those and make sure you can look at pictures and prove them and show them, and look at the limit of Riemann sums to prove them and show them as well. Now, there's a few other things in this section that we need to talk about. For example, we need to talk about the average, which the other math term for that is mean value of a function. We're not going to prove this. You can look. Ooh, what just happened there? Oh, must have zoomed in. Okay. Sorry. Let's try this again. Oh, it's off focus now. Sorry. I'm not really sure what happened there. See if we can get this to work again. Okay, that's just odd. Okay, so hopefully you can read this well enough, so I'm not sure why that's doing that. Anyway, the average value of a function is to find, we're not going to prove it, but it's in your book. So it's 1 over b minus a times the integral. So if you take the area of the function under the curve from a to b and divide it by that delta x space, then that'll give you the average value of a function. And we're not, like I said, we're not going to prove that. It's in your book on page 271. Make sure you look over that and figure that out. Now, this leads us to the mean value theorem. And remember, we had a mean value theorem for derivatives, and that was on page 186, where we said that the derivative, there had to be a place where it was equal to the slope of the secant line. The slope of the tangent had to be equal to the slope of the secant line at some place if f of x was continuous and differentiable. That was for derivatives. But for integrals, we also have an average value, mean value function. And what it tells us is there has to be some value where the function value is equal to the average. Now, if you think about that, that makes perfect sense, because if you take a continuous function and it's continuous along this line from A to B, and you take all, basically what you're doing is you're adding up all these little function values and finding the average. Okay, so we added all the function values, that's what this gives us, and then we took the average because we divided by how many there were, right? And that's, again, in the proof of that average value. And if you take the average, then somewhere along the way there has to be some value where this function value is equal to the average. Okay, so think about that, pause it, think about that, make sure that you understand the mean value and the average value. This is really important. There are lots of questions about average values of functions that you can do. So make sure you know this one. This is one of those things that definitely needs to be on your little spiral of cards to remember for the exam. All right, one last thing. You can relate derivatives and integrals. If you take the derivative of a definite integral, then you get the function. Now we're going to talk about, we're just basically introducing it in this one. We're going to spend a lot of time with this in the next section, but the reason we're introducing it right now is because we have talked about the antiderivative, and what this tells us is that if we take an integral like this and x is our upper bound, then we can find out what that is. It's the antiderivative plus some constant. Like I say, we're not really going to do much with that this section. We will spend lots of time with this in the next section, but I just want to briefly introduce it and make sure it's on. This is on page 273. There's a the exploration there that shows a lot of that. So make sure you've looked over all of that stuff and read this section thoroughly so that we can answer any questions you have in class and go over this further.